Okay, so the the observation. So if you finished 5.1 um, and started on 5.2, um, what we're what we're realizing, we did 5.1 was finding the area under the curve. Okay, and we have that definition for what the area under the curve is, and it is the right. It's the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times delta x, right? So we said the area under a curve is equal to this. This is called, this portion is called a Riemann sum. And this is the limit then of a Riemann sum. And it's very, it looks complicated, right? But really it's not actually that complicated of an idea. I mean, there's some complicated mechanics and notation here, but this is just adding up rectangles, right? The sum of these, each of these are the area of a little rectangle. This is the height and this is the width. And you add them all up and then you let the number of those rectangles go to infinity, and we say that is the area under the curve. And so that's what we have. What we learn in 5.2 is to say, this notation is sort of a lot of extra work. It's hard for us to work with this notation. And so what we can do here is we can replace this part with this. It's called a definite integral notation. So it's like this big S is really what it comes from. So that's a dx. Okay. So this notation in blue is actually really a stand-in for everything that we have here in red. And this definite integral symbol, this big S, is sort of incorporating this infinite sum idea. So what we're really being asked here is to find the area under the curve, because this, so in part A over here, this is really asking us for the area under the curve of this function. And so this is yet another notation or a way of writing that. And this is the notation we'll kind of use moving forward. And it's called the definite integral. So what this first one is doing is it says, it's really, when I read this, I say, find the area under the curve from 0 to 12 of the function. So that's looking at this region right here. Right, what is that area? And if that were a curve, I wouldn't actually know how to do that. Or it'd be very hard for me to do that. But since it's a rectangle and a triangle, I can figure out what that area is, right? There's two rectangles and then this and a half. So there's a total of 4. So that's just going to be 4. Okay. And I think 30 is right here. So that's the same thing. You can break that up and find the area. It gets a little interesting though, or something we haven't talked about, is if I go, what if I go from 30 to 42? So I do this chunk here. Okay. That chunk there is below the x-axis. So if I imagine doing this definition, because that's really what the definite integral is doing this definition, every time I found the function value, that would give me a negative value, right? All the heights there are negative values. So it would give me a negative of what the actual area would be. Now, there's no such thing as negative area. Area is a physical quantity. But we can talk about that, and we will use those words knowing that it's not actually a negative area, but it's equal to the negative of what that area would be. Okay, so if you calculate all the little rectangles and add them all up, you would get the negative of the area of that region. Okay, so this one from 30 to 42 would be a negative. And then from 0 to 54, that'd be the whole thing. I'd have to figure out what this area was. That's positive. And then I would add to that this area, but this would be a negative. Okay. So I don't know, they're not quite symmetric, so they wouldn't quite cancel out, but I would get a number closer to 0 because I'd be adding a positive number and a negative number. Okay, so there's some notation there and some area there. And what we're doing when we calculate this is we usually say that we're using geometry to calculate the definite integral. We're not really using any calculus there. We're just using the shapes and what we know about rectangles and triangles to try and calculate that area. Does that answer that question, or are there any other questions now that we've talked through that? Okay. Other questions? Anything else from homework? Anything else? Okay. All right. So good. I hope that was helpful. So let's just kind of review a little bit of where we were in 5.1 and then talk about what that leads to in 5.2. So 5.1 was just kind of what we talked about just there, that the area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times delta x. And you know, if you were here on Thursday, you should already have seen this about 10 times, right? And so that means it's really important. So you should probably write this down on your notes or keep track of this. This is the definition of what area is. And what we just saw there is that it is also equal to this definite integral from a to b of f of x dx. So it's really the definition. When I write this definite integral, what I really mean is this limit. I do have to kind of keep track, like in this definition, I don't really have the bounds. Remember, a and b are the range that what I'm looking at. I'm looking at the area of that function over there. And so I need to keep sort of track of that in this. So part of this definition is to recognize that delta x is b minus a over n, and x sub I is a plus delta x times I. One other note about this is that this is really equal to what we call sometimes the signed area. So I have area as defined as this definition, and I have the definite integral equal to this. But the definite integral is actually, this function is allowed to be positive or negative. This still makes sense, and we can still calculate this whether it's positive or negative. It may not give me like the area under the curve that I'm thinking of if my function over here is positive and negative, or if it has some different things going on. But that doesn't stop me from actually calculating what that limit is, what this definite integral is. So let's look at an example here. Well, maybe it makes sense just to talk a little bit about sigma notation first. So remember, sigma notation is a sum. We're going to need sigma notation to calculate this limit. So we're just going to spend 5 minutes here just introducing sigma notation. It's a topic that you could spend quite a bit of time on, but we can get what we need to pretty efficiently. Right? So just so we're clear, if I write down this means the sum of i's as i's goes from 1 to 5. So when I is 1, this would be 1, and then it's a sum, and then I move to the next value, which would be 2, plus 3, plus 4, plus 5. Right, so this is like the expanded form written all out. And then of course you can figure out what that is, right? 5, 10, 15. Okay. You could also sum up like a constant from I equals 1 to 6. You could sum up 2. So here, this constant, this doesn't depend on I. It's just always 2. So when I is 1, it's 2. When I is 2, it's 2. When I is 3, it's 2. And when I is 6, it's 2, and I end up with 12. And I think you could see here that maybe that there's a formula there, right? When you sum up I from 1 to n, of a constant, you're going to get that constant times n. Right, so in this case, I'm summing up 2 from 1 to 6. So that's going to be 2 times 6, which would be 12. So this is kind of our first formula that allows us to take a sum and sort of calculate what that's going to be directly. Okay, and that's important for us because I can't actually really take the limit when I have sums here. I need to figure out what the sums actually are. So I need this kind of formula. It turns out there's also a formula for this variety. The way to do it, well, there's a sort of story version of how to do this, but I think I'll just tell you the formula here today. So if you sum up a constant, you just get the constant times n. If you sum up the i's from 1 to n, like we did here, you're going to get n times n plus 1 all over 2. And what it's doing really is it's kind of pairing, like I'm going from 1 to 5. If I pair these numbers together, I always get 6, and I get like half of the total number of things, and they're all 6. It's okay. You don't need to know exactly where it came from. And you should really just think of that as a note or something to kind of memorize. I mean, you should keep track of it probably on your notes. We also have one for the I squareds. That's n plus 1 times 2n plus 1 over 6. And I mean, there's many of these, but all we need is the I cubes. And that's n squared times n plus 1 squared over 4. So, I mean, just so we're clear to see how this works. I mean, this one was easy because I could just write it out, right? 1 plus 2 plus 3 plus 4 plus 5. That's fine. It's 15. I don't need any fancy formulas for that. But if I'm going from like 1 to 100, all of a sudden, well, that's kind of hard to write out. There'd be a lot of work to do the expanded form. And then you add it all together. That's where a formula starts to be really nice. So if this, right, is the same form as this. So n is my upper bound, 5. So this formula says that if I were to do this by the formula, it'd be 5 times 5 plus 1 over 2, right? Which is 5 times 6 over 2, which is indeed 15. So there you go. At least in this case, it worked. It turns out it works in all situations like that. The other rule there's sort of two more rules that are important to us that we use when we're calculating these limits. If you sum a sum or a difference, this would be like AI, BI. This would be like A1 plus B1, and then A2 plus B2, A3 plus B3, all the way up to AN plus BN. Turns out that's the same as just adding up the AIs and then adding or subtracting the BIs. So one way to think of it is that I can, if I have a sum or a difference here, I can just sum each piece individually and then add them or subtract them together. It's not anything revolutionary about, it's just exactly the way that sums work. Okay. And then finally, if I have a constant times a sub I, that's going to be a constant times the sum. So in other words, constants you can kind of pull out in front and multiply after you add everything together. And again, if you write this out, you can see why that's true very quickly, right? This would be CA1 plus CA2 plus CA3 all the way up to CAN. Well, there's a C with all of those, so I can just pull the C out in front and I get exactly this expression. So those are three like rules of sums that we need in order to calculate the limit here that we're going to do. Are there any questions on those? Can you at least kind of, I mean, even if you don't see necessarily where the rule is coming from, which is totally fine, we need to just be able to apply these. So if you see a situation like this, where you're summing the I squareds, you just want to say, oh, I know there's a formula for that. Whatever the n is, I write it out like this. And that sort of takes it out of this summation form and into it's called a closed form. So I know exactly what that is. Okay, so let's try an example here. Let's look at, try and calculate the integral from 1 to 3 of x plus 2 dx. Okay, so this is a definite integral. And we're going to calculate what this is. This is a number, some value. And I'm going to do that by using the definition. So I'm going to take the limit as n goes to infinity of the sum from I equals 1 to n, f of x sub I times delta x. There it is again. And in order to use that definition, I need to figure out what delta x is. So I take b minus a, it's just the length of the interval, and divide it by n, that gives me 2 over n. And then x sub I start with this lower bound where I want to sort of start adding up the rectangles. That's 1. And then I move over each time, and how far I move over is the delta x. And then the I, right, when I'm at the 10th interval, I have moved over 10 2 over n's. Right, so that's how that keeps track of where I am. Okay. So now I need to put all this together. Limit as n goes to infinity, the sum from I equals 1 to n, f of 1 plus 2i over n times 2 over n. And I'm really, at this point, I'm just focusing on this portion. I'll deal with the sum and the limit later. But for right now, I need to figure out what that is. So this is just x plus 2. So this 1 plus 2i over n just goes in for x. And then I add 2 to that. So that's my f And then I'm going to multiply that by 2 over n. Make sure you're distributing this 2 over n to whatever you get here, right? Often this is going to have a couple different terms. So you can't just put the 2 over n on the end. You have to put brackets around it so it's distributed. And I can simplify this a little, right? 1 plus 2 is 3. 3 times 2 over n is 6 over n. Two I over n times 2 over n is 4I over n squared. There's no calculus really being done there. This is just a little algebra, right? I'm plugging this into whatever my function is, and I'm multiplying and adding like terms together until I get to this kind of expression. Okay. Now, the thing to look out for here is, well, notice, of course, we have a sum, and what I showed, one of our properties was that I can take the sum of each of these pieces separately. So I'll go ahead and write that out. I'm writing out kind of every step here. For this one, I would probably be a little more, how do I say it, lazy, perhaps, if I were doing it on my own and not write out every step like this. I is the variable in this case, okay? So when you're dealing with a sum, you can call it other things. It doesn't actually have to be I, it could be J or K. Those are also common. They're called indices. But in this case, it's the I that's changing. So 6 over n, that's not changing at all. Every time that's 6 over n. So this is really a constant. And if I go back to this rule, here, when I sum up a constant from 1 to n, I get the constant times n. So, okay, I can do that. This piece is going to be this constant 6 over n times n. Okay. Here what I have, this 4 over n squared is also a constant, but it's multiplied by I, and I is changing. So what I really have in that situation is I have this. I have a constant times something that's changing, so I can pull the constant out in front. So let me just take a second here and rewrite this. I'm going to pull the 4 over n squared out in front, which is going to leave me the sum from I equals 1 to n of I. And that we have a formula for. That's this one. So this expression gets just replaced with that. 4 over n squared times n plus 1 over 2. And I would say that that step, moving from here to here, is the sort of tricky step in that it's using the summation and the tools of summation, which are not something we have a lot of experience with. Okay. So it's a long process, right? I sort of began all the way up here, right, with these, and I'm still working through the problem. But a lot of it is just manipulating things around. It's only really here that we're using this summation tool in a useful way. And now I'm just finding a limit, which is something we did back in chapter 2, long ago. Right, I'll simplify this a little bit first. This is 6 plus, this is going to be 4n squared plus 4n over 2n squared. So as n goes to infinity, well, this is just 6, right? That's not changing at all, so that's 6. And this, remember, as n goes to infinity, this what matters here is the leading coefficients, which are n squared. This 4n piece actually has no bearing. It's not going to matter. And we had a sort of formal way of doing that. We would divide top and bottom by n squared. It's not necessary for you to do that here. We can use a little shortcut and just say, I can ignore any smaller degrees and just focus on this ratio. And when you do these problems like this, you're always going to get the same, it's always going to be a common leading coefficient, or sorry, a common leading degree. So here they're both n squared. Sometimes they'll both be n cubed or n or whatever it might be. So this is 4 over 2, which is of course 2. And what I end up with is 8. Now, what the heck is 8, right? It's a number. It's a perfectly nice number, but like, what was all this business, right? What am I really getting here? Remember, I'm calculating this definite integral, which we could also figure out what it is by geometry. Because this x plus 2 function is just a straight line. Right? It has a slope of 1. So when x is 1, the y value is 3. When x is 3, the y value is 5. Right? And I want this area. It's easiest to break it up like that, I think. I mean, it's a trapezoid or a whatever. I don't know. It's a square and a triangle. That's how I think of it. All right, so this is 2 by 3, so that's 6. And this is 2 by 2, but it's a triangle, so that's 2. Right? And you'll see here when you look at this, it's sort of almost similar to what we might do with those areas, right? 6 is the lower rectangle, and this 4 over 2 is actually like what you would do for that. So it actually kind of matches. And notice, of course, we get 8. Certainly easier, right, in this case to use geometry because it's a straight line. But as soon as you get a curve like x squared, geometry is of little to no help. Yet this method is still effective, right? It will still give you the actual value, right? So, and the mechanics of this are, I think, pretty startling. What we're really doing is finding an expression for the area in terms of n, right? Where if n is the number of rectangles. So when I go through all this work and I get to here, this expression right here is really the area if I come up with 4 rectangles or 10 rectangles or 100 rectangles. If I replace n with those numbers, that's going to give me the area approximated by adding up those rectangles. And what's amazing is if I can take the limit then, which I can, it actually gives me a value. So 1,000,000 rectangles won't get me quite to 8. It'll be really, really, really close, but it won't get me there. But the limit tells me where those are going towards, right? It tells me the value that I'm heading towards, which is 8. Are there questions about this process or any steps? Like I said, it's not that any step is particularly hard, maybe, but there's a lot of steps, right? There's a lot of things to keep track of, and we're working with some new notation, right? The sigma notation, and a lot of small algebra steps, which make it easy to make little errors. Are there any questions from any step that I can help with right here? I go through another example in the sort of mini lecture on this in D2L, so you'll want to, I would encourage you to watch that as well. These are pretty important problems, so you should expect, you'll work through one of these on the take-home work, and you'd expect to see something like this on the final exam as well. So it takes a couple runs to kind of get the process down. The good thing is that sort of all versions of this really lead to the same general structure of how we work through it. Sometimes you'll have 3 terms instead of 2 terms, or I-squareds instead of I's, but underneath that, it's really the same problem each time. Okay. No questions? it makes me nervous, but I hope that's a good thing. You know, if we're in class, I can see the sort of panic in your eyes sometimes, even if you don't ask a question. But here, you know, I can't get through your bluffing, right? If that's the case, and maybe you do think you've got it, and that's great, and maybe you do, and maybe when you start doing the problems, you'll think like, okay, I thought I got this, but now it seems a little harder. That's totally part of the process too, right? So don't be alarmed, and ask for some help if you sort of lose the train of thought as you try and attempt these on your own. So, you know, again, 5.1 and 5.2 are really close together. I mean, when I think about them, I sometimes have trouble even remembering which, what is where, right? Which sort of topic is where, but we definitely talk a little bit about the definite integral. We need to talk a little bit more about that and some of the properties of that expression. So that's in many ways what we are going to spend our time with here for the last couple weeks that we have together, are learning some more things about the definite integral and learning sort of what it tells us. And we know right now it gives us kind of area, air quotes around area, because it's like we said, it's a signed area. So it's only positive if it's above the x-axis, right? And it's negative if it's below. And if it's a little of both, then it sort of just adds all of that together. So the definite integral, it's not like a smart thing. It just does what you tell it to do, right? And so what we're telling it to do is add up all of the rectangles between A and B. And when you do that, you can learn some things about it, and we can interpret this or come to some intuition about it, both from area and from the definition. So remember, this is also area, and it is also the definition. We will learn a third way to do the definite integral when we introduce 5.3, and that's a really powerful tool, but we're not quite there yet. So here, let's just look at some properties. So what about if I go from A to A? So my upper bound and my lower bound are the same. What do you think that's going to result in? And again, you could think about this by remembering what the definition tells us and does, or you can think about it by trying to interpret it in terms of area, right? What would the area of this kind of tell us what to do? Yeah, exactly. So it's like I'm going from A to A. So if I'm thinking about it in terms of area, I'm not really moving anywhere. So if I were to kind of add up all the area that I get by not moving, you know, how much area would I get? I wouldn't get anything. Exactly. Zero. Big fat nothing. Okay. So that's like a rationalizing about it by area. We could also, if we think about like a definition, you know, in your definition, you have delta x, which is b minus a, which in this case would be a minus a over n, which would be 0. So in terms of your definition, you'd be multiplying everything by 0 and adding up a bunch of zeros, and you would also end up with 0. Okay, so a lot of these properties you can figure out or have some intuition about, and that's helpful. But you can also remember them just as properties. So if I do see that integral from A to A, I just automatically know that's 0. I think a lot of people remember that by thinking about it in terms of area. Just think I don't move anywhere. That means I'm going to get 0 area. Let's try this one. The integral from minus a to a of f of x dx, if f of x is odd. So remember, an odd function is symmetric around the origin. And if I go from minus a to a, can you see what's going to happen there when I add this up? And again, this is kind of thinking about it both ways at the same time, I guess, right? The definition and area. I'm going to add up all of these rectangles, and I'm going to add up all of these rectangles. And because it's odd, it's symmetric. So this area is exactly the same as this area. But because this area is below the x-axis, this is negative, and this area is positive. Since they're exactly the same, when I add them together, I mean, they're opposites, right? They're one's positive and one's negative. They're going to cancel each other out exactly. And again, that only works when the bounds are exactly from -2 to 2 or -pi to pi. As soon as you go from like -1 to 3, then kind of all bets are off. I don't know what that would be. It wouldn't be 0. And it also only works when I have an odd function, right? One that's symmetric. So, part of the goal here is to recognize and start to get comfortable with this notation, right? What is this really telling me, this definite integral thing? And the more we use it and think about it, the better off we'll be, right, as we move forward. So a lot of it is just getting comfortable, and then we can, notice what the bigger issues are. So those are two properties. So here's another one. What if I sort of flip the bounds around? Are those going to be equal, the same thing, or some half of this one, or some relationship between those? It's not really clear at all from area, because changing the bounds around doesn't change the area at all. It'd be technically the same area. But when we're doing this calculation, remember delta x is the b minus a, which is really the upper minus the lower. So for this one, delta x would equal a minus b. But for this one, it would equal b minus a, right? One of these is positive and one of these is negative, but they're opposites of each other. So every value that I add up is going to be the opposite if I did it in this other direction, right? So it turns out that the integral, however you want to think about it, you just end up with the negative. Okay. So if you switch the bounds around, it does impact it. You get the negative of what you would have gotten the other way. That one to me always feels a little counterintuitive when I think about area. Because if I imagine going rectangles from right to left or left to right, they should kind of be the same, right? But they're not because of how we do the calculation. So the order of the bounds do matter, but only by a negative. Okay, one more here. I think one more that kind of matters. So the integral from a to b, it turns out, can be written as the integral from a to c. Sorry, that should be a plus. The integral from c to b. In sort of a straightforward situation, that actually is pretty likely. If this is a and this is b, if I put c somewhere in the middle there, certainly makes sense that if I find the area from a to b, that would be the same as the area from a to c plus the area from c to b, right? It's really just splitting that into two pieces. It turns out it actually works even if c is not inside the interval. C could be the larger value. You end up with some like negative areas that kind of cancel each other out, and it works out that way too. And f of x can be positive or negative, right? It doesn't have to all be above the x-axis. But this one I think is probably best thought of using area and using this kind of visual example. Okay, so those are some kind of, think of them as maybe shortcuts for definite integrals, kind of how definite integrals have to work given how they're defined, and give us some tools to kind of find or work with definite integrals without calculating them directly. At the moment, calculating them directly is actually pretty challenging. We sometimes could get lucky and know what the area is, right? If we're working with a rectangle or maybe a circle. Well, that's one thing I do want to mention. You know, the square root of x squared minus 4 is equal to the top half of a circle of radius 2. Okay. So that's one that comes up. I'm just kind of mentioning that as a special case because the book kind of likes to use that one, and it looks like maybe a really complicated function for us to work with by the definition, but we can instead, because it's a circle and we know the area of circles, you can figure out the area right under that curve by geometry. So you can do rectangles and triangles and circles with geometry. So that's possible, right? You get lucky that way. But otherwise we'd have to use this definition, and the definition is pretty hard to do, right? We did this one example here, but that certainly wasn't trivial, right? And that was from, actually, it turns out, a very simple function. It doesn't always get more complicated as the function gets complicated, but a lot of times it does. So what you should be sort of thinking now is like, okay, well, I can sometimes find these definite integrals, but certainly not always, and not always efficiently. Luckily for everyone involved, there is a better way of finding these values, and we're going to talk about that when we get to 5.3. Okay, so right now, just be clear on these two methods, and those are going to be useful for us too on exams and work. We can use geometry because we know what that definition is telling us, and geometry can answer that question. And then we can also use the definition. And I will usually tell you, I think always tell you what I want you to use. Right? So if I say use the definition, then of course that means use the definition. And if I say geometry, well, you should be then able to figure it out by geometry, right? So at this point, we want to be comfortable with those two styles. Any questions on those examples or anything that I've talked about? I mean, I think it's one of those things that you may or may not kind of know, like maybe if you're like, okay, yeah, that made sense what you were saying, but then when you go and do the work, all of a sudden it feels a little different, right? And that's certainly possible here. There's a lot of different steps. All it takes is kind of one little mistake to get the wrong answer. Then it's hard to know. I've had a couple people ask me some questions on some of these problems, and they've gotten like 98% of it right, but there's like one little thing they have off, and so of course they're not getting the right answer, and it's hard to know, right, what's wrong there. So please ask me those questions so I can help steer you efficiently into getting the right answers and the help you need for those. And again, the goal here is to build our kind of fluency with this definite integral, to kind of understand what it means and what it's doing. And we will start to connect some more ideas when we do 5.3. That's a pretty important, it's called the fundamental theorem of calculus. So it's got a big important name, and it is an important topic for us. So we're going to cover that on Thursday. So I'd really I know you only have to be here for one session, but I would really recommend being here on Thursday if possible, to go over that. If you can't, I'll record it, and that's still pretty good. But it's going to be worth looking through because it's going to connect our ideas of the derivative to this definite integral. I think it's pretty awesome.